Well, good afternoon, everyone. Hope you all are doing fine today. Just to give you, I think you all already know, we're going to start off with going over last year's test. Is kind of what we're going to go over, which should be relatively quick. So after that, I can probably take questions and at least attempt to help you at least start somewhere for solving some of these problems, I guess, from Homework 6, which should just be really good. Do you all know when are you supposed to turn that in for your final?
Yeah.
Is it doing homework? So the first problem is a continuous systems problem. I imagine he'll probably do something pretty similar to what we did here in this test in terms of the kind of problems he'll give you. So there was a torsional system. I'll kind of draw a picture. I apologize for my drawing capability. I didn't pick to be a artist, to say the least. So ultimately, it's a torsional system, except for you have some sort of inertia turbine at the end. So what you're looking at is a propeller shaft of, you can say, a boat or anything of the sorts. So you have various properties. You can say this is your x direction. This is going to be L. This is going to be a rod, and we'll define some of those characteristics here. It has a diameter of 5 centimeters. It has a length of 1 meter, which makes that nice. The mass moment of inertia of the propeller is given, so you don't have to try to figure that out. And then we're given other properties, such as density as 7,600 kilograms per meter cubed. And then we're looking at G, which is 80 pascals. And finally, he gives two equations. The polar moment of inertia of the rod is going to be 30 pi d to the 4 times divided by 32. And he also tells us that tangent of alpha is approximately alpha if, and really only if you want to say, alpha is less than 1. I'll just say if. So that's kind of the initial problem he gives. So I guess I'll ask a question. Where would be the first place to kind of start? Or where would y'all start? That's actually a good point. So this is this value. It's determining the fundamental frequency of the continuous system. And really what you're looking for is the first fundamental aka the fundamental. You're looking for the first natural frequency is what you're looking for, which is what the fundamental part tells us. So what is the first equation that you guys will look for, or at least similar equations? Obviously, you know it's a continuous system. Do y'all have any ideas? I'll give you a second just to think about it, just to see if anyone can come up with it. Any ideas?
What is it again? What's rho? Is that the density?
Rho, that's the density. Yeah. So not all of these parameters are going to be found in your initial set. Know that you'll see some of these parameters start to show up as we go through the solution. So really, the first thing that you're looking at is you have this relation of this is going to be equal to, which could be found in various books. I use, which actually I don't think many of you use this book this year. I think most of you use either Thorby or the RAL. I was using this book. It's in here also. But I'm not sure if he even showed you guys that book. But it's definitely in various books, and it may also be in your notes. We're looking at. So we're looking at the twist, because we're looking at it. That's why we have the inertias. But is we're looking at the twist of this system instead of like bending or those other kinds of modes. So your first theta solution, where would you go with, what is our solution for theta? What is our general solution for theta? And this is pretty much irregardless of the system you have. It's always going to be the same. So sine, cosine of something. So we'll start off with C1 cosine kx plus C2 sine kx, and then that'll be 1, and then we'll do, since this is a multi-dimensional problem, I guess in that sense, time and this. So is that what you would expect to see?
Shouldn't one of those be functions in time?
Oh, actually the right side is the function of time. Yeah. So this is a function of time. One of the first things you could do is note what your boundary conditions are going to be for the boundary and or initial conditions for the problem. So for this problem, what is theta at, we can even just say time at the x position of 0 of any time. 0. So that'll help us out a little bit later on, and I'm actually not sure if we need anything else beyond that to solve this problem. Because what does that tell us immediately here? So if we say theta, well, we'll get there. Okay. From there, there's a condition. Basically, this is kind of an applied torque in that sense. So we'll get there. So you do have theta and L, or theta being, or I guess L being there, but your theta isn't going to be necessarily 0, because even with some sort of inertia based on when you put that on, it's going to twist already without any kind of vibration. So we said with 0 position, so we go through this C1 cosine 0 plus C2 sine 0. C3 cosine omega t plus C4 sine omega t equals R0. Correct? Therefore, this sine 0 is going to be 0, so we can ignore that term. And then there's something nice kind of about this, is we could actually just consider our position in this. So we look at C1 is equal to, we divide this out, just that whole term out, and we should be able to get C1 is 0. So that solves that one coefficient. So now we're not worrying about this at all. So as we begin to take derivatives of our equation of motion, you don't have to consider C1 anymore, so you have to carry that all the way through. So what's your next step? Okay, so find another boundary condition. So really what this is up here, I should say, is more along the lines of, so at L, this is pretty much always what you're looking at. Saying your change in position is going to be related to the second derivative of your change in time with these. Yes?
What is alpha? What is alpha?
Where do you see alpha? Well, again, we'll get there. That's why I was saying
in this solution, you'll see parameters show up. And we'll kind of talk about this. This is just important to note. We're not, well, actually, we don't even have to have an alpha in that. That's just some arbitrary saying tangent of some variable. If that variable is super small, is just going to be that variable. Yeah, which is just going to help us solve this later on. Because eventually, what you're going to find out is we're going to come to a point where we have a tangent, and then to make the problems easier, we assume that it is small. You don't actually have to assume it's small. I don't think so. I think one of the books kind of goes through the actual solution of, you'll see when we get to that point, but it goes through a solution similar to that where it has a number of solutions for what if you had a different right side. So first, we'll try to find these derivatives, because now we have our L boundary conditions here is really what we're looking at. So if you want, you take theta, and we want to find d theta dx. And I'm going to try to spare you the actual derivation of this, unless you guys want me to, but I'm going to assume that y'all can figure it out. So it's C2k cosine of what, kx, right? Which, so you have this multiplied by, again, our C3 cosine omega t plus C4 sine omega t. And do y'all see why the cosine sine omega t aren't touched by this? Yeah, there's no x in there, so therefore you don't take the derivative. Fairly self-explanatory. And then we'll go to the second derivative, which obviously isn't going to touch this. You get C2 sine kx. And feel free to slow me down at any point in time if I start going a little too fast. I do think a little fast sometimes. But if you get omega squared C3 cosine omega t minus omega squared C4 sine omega t here.
That's d squared dx, right? Second derivative is dx.
dt.
Well, you just took the derivative.
This?
They're separate.
These are two different separate
Oh, okay,
equations.
never mind.
Because we have two different separate equations we need to solve for.
Yep,
You have
gotcha.
d theta dx and
Yeah.
or delta theta dx, and then the second derivative of this. So now you have two equations. You have your boundary conditions. Now you can implement them into each other in such a way that you'll get what? G, J, C2, K cosine of K times X times C3 cosine omega T plus C4 sine omega T equals our negative J naught, and we'll multiply it by a negative omega squared, because we're going to pull this negative omega squared out of here and put it as some sort of coefficient. That times this whole equation here, which is C3 cosine omega T plus C4 sine omega T. And from there, what you can see is both of these sides can cancel out. So this is now, you're eliminating the fact that it's a function of time, and now and then this has a sine, or C2 sine kx, by the way. Yeah. That cancels out, C2 cancels out. Now you're left with GJ, GJ K cosine kx
equals omega squared J naught sine kx. Can you all see how that progresses? So from that, now you have what you're really looking for here. And this is where ultimately you want to get this kx to one side, and that's where this next part kind of comes into play. Does everyone have this written down? I'm going to erase this side and start working kind of over here. So what you have here is now you can divide by the cosine and get your tangent, and now I'm going to maneuver all of the constants over to the left-hand side. So then we'll get tangent of kx is going to be equal to gjk over omega squared j naught. And this is kind of where that alpha comes into play. So we have a method for, if you haven't seen, we have k and k on both sides, and ultimately what we're really trying to find is this omega. And that omega is on the left side also. So you could use some sort of kind of iterative solution, so some numerical solution to find it, or they have a method of doing this. And that is, if you get alpha tangent alpha equal to something, some books have a table that has this solution for some value on the left side, or we could actually solve this using this assumption here that tangent alpha is approximated to alpha, because then you end up getting that this is alpha squared. So, and something I didn't note also, by the way, this x, which I forgot, I said over here earlier, this x isn't x, it's actually going to be the L, because we're looking at this as a boundary condition. So that's actually all L from there. But before we get to the alpha squared, we'll keep it in the tangent form. So we know that we want this to be alpha, so tangent KL. So we have to have some way of getting KL over here. And so we're going to be looking for KL tangent KL is going to be equal to GJ, because now I'm going to, since I moved this, since I have KL over here, I'm just going to multiply KL to both sides, K squared L over omega squared J naught. And now we have it in a form where we can see, now we have it in some sort of alpha term form here. Now what is K, yes?
Can you talk more about how tangent alpha changes to alpha tangent alpha?
So ultimately we have, this is tangent alpha is KL. What I did is we know we need it in some form that's alpha tangent alpha. So that's, we know that a lot of these solutions are going to come down to that solution. Have you guys gone over that? If not, you'll see that, maybe not a lot of them I should say, but you'll see that a few of them are. And some of the books have an actual table to solve what alpha tangent alpha is based on what your left solution over here.
Multiply both sides by KL.
Yeah, ultimately that's what I did, is just to get an alpha tangent alpha form, which is what we need next. Do you all know what K is? So omega over C, and for this particular case, you should be able to find this in the book. C is going to be equal to G over rho. So now that's where we just introduced rho into our solution. I believe that's correct, right? I have to see. C. Yeah, C is equal to the square root of G over rho, which now we know if this is K omega C, we could switch it to this form where we have, I'm going to get rid of this now, where you have omega C L tangent of omega C L, and I'll kind of move around here, saying GJ omega squared C squared L over omega squared G naught here. Then from there, what you could do is you could actually get rid of this omega squared, so it cancels out on the right-hand side, and that's how we just eliminated that entire, how we eliminated omega from the left side, or the right-hand side, and got it to the left. Does that follow? Then from there, we move forward to now we could just say alpha is going to be equal to omega c over L. We'll just leave it like that. And now I have it in the alpha tangent alpha form that we're looking for. What we can do next is, since c squared is actually going to go down here, and we can plug in that rho over g so that we get, do this.
For alpha, is it omega L over C?
Or it's omega c times L. Or omega L times over c
Okay.
is what you can. I write it like this form, but it doesn't have to be. You can do omega L over c is what you really can do. From there, you get the alpha tangent alpha form, which then you're going to get G over L. Yes.
Is there supposed to be a negative j on the right-hand side?
No, because there was a negative omega squared here. Negative j naught times negative omega squared is a positive.
Oh, okay.
And then you have this c squared will actually, divided by c squared is going to give you the inverse of this. So you end up getting a j naught g down below. And then what you could do is you could now cancel your g, and now you're left with this system of alpha tangent alpha equals j L rho over j naught. From here, that's where we use the simplification that tangent alpha can be approximated to alpha if alpha is far less than 1. So we're going to assume that now, and from there you find that, am I going to erase this? You have this all down on the left side here. I'm not going to erase this, I'll keep this. But from there, you're able to follow that tangent becomes alpha squared, and then you get j L rho over j naught. Right? And one quick way of kind of looking at this, j is the polar moment of inertia, so it's supposed to be units of m to the fourth. You have an m, so you have m to the fifth here, times kilograms per meter cubed. So you're going to get kilograms per meter squared up here, and then j naught is in a unit of kilograms per meter squared. You kind of got to check yourself at this point in time, because this has to be non-dimensional, because alpha is non-dimensional, and the way you can tell alpha is non-dimensional is because it's put into tangent alpha. So tangent alpha has to be non-dimensional because you can't plug in like a tangent of 1 meter cubed into there. Does that make sense? And so a gut check here would be telling you that. Now again, kind of easy, basic, JL rho, J naught. Is what you get. But now we can convert alpha back to what we originally had as omega c L equals J L rho over J naught, and you can begin to start simplifying the problem to find omega. So omega is going to be equal to c over L, and now we can even plug in J into this, which we have, I erased it, but J was equal to pi d to the fourth divided by 32. And that's the polar moment of inertia. And we can plug that in, pi d to the fourth L rho J naught. You can get to this solution here. But we have C, and we know C is the square root of G over rho. So we can actually plug that in where you get G pi d to the fourth L. Rho is going to end up canceling, but I'll write it here. You get 1 over L, and then 32 here. 32 J naught times rho. Anyone have any questions about that?
So if you don't have a small angle, or you can't apply the small angle approximation for alpha, you said there was a table in your book or something?
I believe, don't quote me on that. If there's not, there are tables that exist, not that you need them for this. If you wanted to solve this exactly, you can do that. Or later on, you could do kind of more of an iterative solution in the sense that you look at this. I know for 301 it's similar to what you do for like boundary layers. You look at this, you find a number, you get whatever omega you're looking for, your fundamental natural frequency. Then you can plug that back into alpha here, and if that, you can find out if that approximation is a good approximation or not. If not, then you could use either some sort of numerical solution for this, or again, there is a long mathematical solution, but they usually just give you tables of alpha, tangent alpha, and its solutions for either some alpha to this or to some this to your alpha.
So for things that kind of pop like this on the final, it's probably safe to say that you can use that small angle approximation?
Yes, especially, I mean, that's what he wrote on the test. Is tangent alpha is equal to alpha if this. So he's trying to point out, Noxier is fairly good about doing that. And he's going to point out that, like, hey, if there's a small little trick in there, that's something simple like that, he'll throw it out there to make sure that you don't get messed up necessarily on the math. You go straight for that. Yes? Well, J is the polar moment of inertia, so that's like, if you cut it, that's like your structure stuff. You find your polar moment of inertia, or your area. It's an area moment of inertia. Yes, but since it's a rod, and a rod circular rod, you have polar moment, which is J. Then from there, J naught is the mass moment of inertia of your propeller. Is kind of your difference. Yes.
At the beginning, how do we get the equation that Gj d theta over dx is equal to negative J naught?
That's also initial condition kind of equation, because we know this is kind of a torque. I know where it's in this book. Unfortunately, I don't know where it is in the others.
That's an equation that we need to know or to derive.
Yes, and I'm not exactly sure where they derive it from in that sense, but I can figure that out.
Hey, Wayne,
Yes.
what is J naught?
I know you said moment of inertia was J, and then.
Well, J naught is the mass moment of
Oh, the
inertia
top, right.
of this, about that axis that it's twisting.
Oh, okay.
So generally, this wheel or something at the bottom, you'll have, like you said, a lot of times you'll even have tables for. I mean, I think the book. I'm not sure if this book has it. I know Thorby has a little bit better table for it, but it'll give you even what kind of boundary conditions you can have, and so that'll show that is your equation for your boundary conditions. A lot of times they're derived from various ways. This book kind of goes over it, but then they don't completely.
Should we just use that table?
Yeah, for actually a lot of continuous system problems, that's what you're going to do, is just use a table to find your solution in that sense. Because finding, I mean, obviously solving for some of these equations is fairly difficult in that sense, and timely. Did I see another hand, or was that kind of answered? Yes.
So this is the first natural frequency?
Yes, and in the problem he says, look for the fundamental natural frequency. If you didn't want to look for the fundamental natural frequency, you would solve for this omega, and then you're going to have some sort of n over here, so that you'll have like your second natural frequency, your third natural frequency, fourth and fifth, because you're going to resonate at those different natural frequencies. Yes. Or did you? Oh no, okay. but we're just looking for this initial one. So it's going to be some multiple or half multiple of this. And to kind of just continue on, I mean, give you kind of the final answer is going to be omega is equal to 1 over L times G pi d to the 4th L over 32 J naught. And that's going to be your final solution. And if you plug in all the numbers and change all the units, you'll get roughly 70.06 radians per second. And that would be all your last number. I mean, if you want, I can plug that in, but I assume that saves us a little bit of time in avoiding that. Yes?
On your omega step, you went from omega equals C over L, square root all of that equals 1 over L. Where's the C?
No, this is C. This is C.
But where does this C go?
Well, you went to 1 over L.
Well, C is
Okay, I was like,
G over rho. And if you multiply a square root times a square root, you could just put them in each other. And that's where you get this G, and that's where you get that rho. And from there, so after that, we'll kind of go over the next problem, if that's good with y'all. And so the next problem he gives is a response of a multi-degree of freedom problem. And so the next one is a box inside of a, or it's actually, well, it's a box on wheels, which begins with a circular mass here. This is kind of, and then force being applied here, force being applied here, and then we have a spring here, and we have a damper here, and some wall. So now you're looking at a fun problem. Just kidding. But the nice thing is he already solves the equations of motion for you, and he'll do that often for something like this where he wants you to get the idea behind that. So kind of the first test was most likely more of like you solve your Lagrange equations, and etc. This time he'll probably give you something similar to this where he'll have a solution already there for you, and that being
Is that spring attached to the middle of the?
yes. Again, I'm not a good artist,
Just making sure.
to say the least. Yeah, let's avoid that because I'll leave that to others. And oh, your coordinates are x double dot and theta double dot, or theta and x, c1 0 0, c2 x dot theta dot, and then plus k1 0 0 k1 r squared, and I'm just going to put some vector z, which is just the x and theta, f1 plus f2, and this is negative f2 plus r, or times r, are your two equations. And then he kind of fills this in he gives you what the mass is and the radius. So he does actually quite a bit of work for you for all sense. And he even ends up giving you u. I'll kind of just skip down to u right now. He shows you that u is given as 1, 1, negative 0.5125, and 10.5125. So he gives you your modal matrix. He even actually gives you the inverse of the modal matrix. Sorry, did I? Oh, I just made z. Z was, I probably could just do z equals x theta, and then just to make this shorter, I was just trying to make it shorter, but this is z double dot. So you're looking at that's your state vector is z. Now I just said z dot, where z is x theta. So anytime you want to plug in z, you just plug x theta, x dot theta dot, and x double dot theta double dot into there. Yes.
Also, is there a negative in front of that F2 line? Or is that just your line, your bracket?
That is a negative.
Okay, cool.
Again, which he gives you kind of all of this here. The things. Your mass matrix will be 16, -1, -1, 0.15. Your C matrix is 5, 0, 0, 0.05, and your K matrix is 100, 0, 0, 1. Yes. So those are the various things he gives you. And the first question he asks is, so find the modal mass and the modal stiffness and dampening frequency. Yes.
Where is mass 1?
Oh, well, it's the mass of this thing.
And what's a C2?
C2. Well, he gives you these equations, so what I'm assuming is it's some sort of it's some sort of like friction of your roller or something. He's just saying there's dampening associated with it. Because he just gives you, he literally says, here's your system, then he gives you this equation, he gives you the matrices, even though he just gave you all the masses and everything, so you plug those in, and then he gives you your modal matrix and the inverse of your modal matrix. So he's giving you quite a bit from there. And from there, the first question he asks is, well, let's find the modal mass. So M tilde, K tilde, and C tilde. Yes?
Inverse u, the bottom left number is -0.475.
Yes, 0.475. Yes. And so the first part asks you to solve for M tilde. So how do you solve for M tilde? Times U?
Yeah.
Cool. And then, so now you can do the to be honest, I think you can do the matrix algebra. From there, transpose, you should get 1, -9.5125, 1, and 10.5125. Do you have any issues seeing stuff over there? Sorry, I'm drawing a little slow. Do you need this? What are you missing?
The K matrix?
Oh, so K is equal to 100, 0, 0, 1. Do you need anything else over here? Or okay. From this, I mean, continue forward with your mass matrix at 16, -1, -1, 0.15, and 1, 1, -0.5125, 10.5125. And so from here, you could either do the matrix algebra, which you'll start multiplying these two matrices, you'll get the 2 by 2 again, and then you'll multiply that 2 by 2 by this, or you can just plug it in your calculator. Something a little bit simpler in that sense. But just for the sake of, if you want to go through this, and your modal matrix is going to be 48.5, we'll say 48.6, 0, 0, and 11.55 is your modal matrix. And then you'll go through that with K, and you'll go through that with C. And I'll just go ahead and put those up there unless you want me to go through that. Would you like me to go through that? So K tilde, 90.5, 0, 0, 11. C tilde. Does anyone have questions about this?
Oh, wait, because it's low.
Oh, well, it's K is going to be 190.5. This is 0, 0, and this is 210.5. And that's K tilde.
Yeah, I wish all of the questions were. I know. I would get it.
So he kind of gives you this, and then now he says to solve for your natural frequencies. How do we solve for our natural frequencies given the modal matrix? Okay, so I see where you're going. So you said K inverse M, or something along the same, like along those lines. But
Something like that.
what is nice about the modal form? So it's decoupled. So if you looked at this as M, C, and K, you looked at those in a line, you have 48.6 is your mass, 99.5 is your dampening, and 190.5 is your K. So if I want to, and this is for the first mode. So if I'm trying to find my first natural frequency, what is the equation of natural frequency? Square root of Km. So if I'm trying to find my first one, I'm going to look K1 and M1. And that's kind of the nice thing with this, is you can literally just take this 48.6 and you can take this 190.5, you plug it in, you're going to find that you're going to find that's roughly 1.98 radians per second. And then you do the same thing for omega 2, where this is K. And if you want, you could do K11, M11, and then K22, M22 for to show what your positions. This is K11, K12, K21, K22. But we're not necessarily worried about that, but you can show that. And then you're going to find that this is approximately 4.27 radians per second. So that's the second question he asked for. Then part C, he's going to ask for what your dampening ratio for your first problem is. So how are we going to find the dampening ratio of our first one? Yeah, compute the dampening ratio for mode 1 of the system.
We have alpha. No, we already had
Do we need alpha or beta?
No.
So if we were just looking at a single degree of freedom system, what is, so if we look at a single degree of freedom system, we have 2 zeta omega n x dot plus omega n squared x equals something, right? So with this, then how do we find our zeta? C. Okay, so now we go back to here. Again, C is in that same 0, 0, this form. And that's why you always use Rayleigh dampening as your estimation for damping in a system like this, because when you multiply it times that modal matrix C, you're going to get a diagonal matrix, which then lets you easily solve this. So zeta is then going to be equal to your C1, or zeta 1 is going to be equal to your C11 divided by 2 omega 1 is all it's going to be, which is going to be 9.5 divided by 2 times 1.98.
But shouldn't you divide math? Because your coefficient for your x of y isn't 1.
One second. Where am I seeing this? Let me see this really quick.
No, this is the original one.
Oh,
This is
oh,
already with the-
Yeah, but we didn't have.
that's right, that's right. You should, and actually, that's a good point, is you will have a mass, is because I guess this isn't necessarily in that form, and you're right, there is a mass in there. So you get x, or zeta, is equal to, because you have some mass here, and you have to divide that mass through. To get into this actual form is where you're really looking for. So zeta is going to be equal to C11 divided by 2 omega 1 times M11. And then that's how you're going to get that solution. You'll find that zeta 1 is approximately 0.05 or 0.0449 if you want to go with that. Then he wants to have you find your, well, let's see. Does that make a little bit of sense? Because what zeta is, actually if you look at the definition of zeta, it's going to be C over 2 square root of Km. Oh, this is square root. My bad. And so it is going to be square root. So you can't actually use it in this form here because this isn't, what we have right here is C divided by M is what you would have to have here. So you could say, yeah, I don't need a square root. If you're multiplying by omega, but the definition here is K times M. And if you looked at what omega is square root of K over M. If you do the math, then you get the square root of M here, if you did it in this form. So you could, but since you already solved for omega, you could just plug this in, or you could just use this. They use the same amount of variables. So next, he gives you a system as if both of the F1 and F2 are zeros. Do you guys have any questions on this? I guess I should first stop it. We're good? So, and so from there, he's going to ask what the modal response is going to be, corresponding to some initial conditions. His initial conditions, so again, my z, I'm going to define, z's defined here, so I'm just going to write this like this. As this is going to be 0, and then z dot is going to be 1, 0, so that's your initial conditions. F1 is equal to 0, and F2 are both equal to 0.
What are we looking for this part?
Pardon me?
What are we looking for this part?
For the case of the external exciting force, F1 equals 0, F2 equals 0, he gives us our initial conditions. Find the corresponding initial conditions in terms of the modal coordinates. So what is Q? And what is Q dot with these initial conditions? So how do you find Q if you're given X? Pardon me? Multiply by U or U inverse or U transpose? U inverse. Good.
So now you get U inverse times X, which, if you want U inverse, he gives you, again, 5250, 0.4750, negative 0.0499, and 0.0499 times our initial conditions, which are going to be 0 and 0, and you could solve for that to be 0 and 0. Simple enough? But then the next one, you're going to have a different Q dot, because your U inverse X dot is the next initial conditions, is just this transpose times the 1/0 here, and you're going to find 0.525 and 0.475. So those are your initial conditions for your modal matrices. Does that, again, also make sense? Sorry, I'm kind of skipping over the math, but again, I kind of assume you all can get there yourselves. And the last thing he asks for is using the method of modal analysis to find the response for x of t and theta of t to the initial conditions described in part D. To reduce the total amount of work you need to do, compute only the part of the response which is due to the contribution from mode 1.
Anyway,
Yes?
going back up top, is, I think U inverse, the bottom left is negative?
I don't think so. Oh, look. Not what he's given. It's negative 0.049 on top, and if I wrote negative, I didn't mean to.
So there's only one negative in it?
Yeah, there's only this. Oh, you said bottom. You say bottom left?
Yes.
Oh, just kidding. I thought you said bottom right.
So does that mean that Q dot is negative on the bottom here?
Not necessarily. Yeah, it is. Okay, yeah, it is. From that, you could get, from this, you can find what your Q1 is going to be e to the negative zeta omega n times time. Yeah. So, and he wants the contribution of the first mode only, so it's going to be just t. You say a cosine omega 1 t plus b cosine omega 1 t here, and then Q2 is going to be e to the, are we only looking at that? Oh yeah, and so we're only going to look at that because we're only looking at the first mode. So you're not worried about Q2 from here. And now how do we go, if we're given this, you can solve for Q1 and Q2 using your initial conditions here. Or you can solve for A and B. You'll find that A is going to be equal to 0. Oh, and these are omega D1 and omega D1 from there. And from there, you can solve for A is equal to 0 because your initial condition for Q1 is 0. Yes? Do you have something? No?
No, I was just trying to follow where you went from there to there.
From where to where?
From the Q matrix all the way to the first one, back to the top.
Oh, up here?
Yeah.
Well, from up here, you're just looking at, well, this is just your solution. All you're looking for is you're trying to find, you use this to find what we're trying to find the equations of motion for x of t or your response of x of t and theta of t.
But since we have modal coordinates, we could solve it in terms of modal coordinates and then transpose it back to
Yeah.
the theta and x space. And then using these initial conditions is what I was saying, is that q is equal to 0, 0. You get 0 here, you can plug it in, you find that a is going to be equal to 0, and b is equal to roughly, and b is roughly equal to, I actually don't write down exactly b here, but b, by the way, this is sine. 0.266. And then you know what your dampening is, and you know what your omega 1 is, and you now just solve this down to e to the negative zeta omega 1 t b sine omega d t, d1 t. So now you have this as just your equation of motion for q, and then x of t is going to be, and we're just by the way, we're only looking at the response of the system, the contribution from the first mode. We're not looking at the contribution of the second mode. That's why we only have to solve for q1 instead of having two equations, which would be q1 and q2. And from there, you could find, or x, which now x is going to be, or x of t is a vector of x and theta. You find that that is going to be equal to the first modal coordinate times t, and now you kind of have your solution for the system. And so you could do, if you want, you could say U2, Q2T, if you want. But this is just going to stay as QT, and you can show that at least there is some sort of contribution from the modal coordinate of 2. U1 is going to be, oh, I don't have it up on the board anymore, but it's going to be the first column of the modal matrix C that you were given. Any questions about that? And I could write down a final answer if you'd like, but I think that's fairly self-explanatory.
So the U1, Q1 is the effect from the first mode?
First mode, yeah, and we didn't have to solve for the second Q2 because Q2 is only going to be including the second mode. Yes?
Could you explain a little how you got the A and B?
You use your initial conditions. So our initial conditions are 0, 0, but since we're only looking at our first, you can put Q1 is equal to 0. 0 at a time of 0. So 0, e to the 0 here is 1. A cosine 0 is going to be A, plus B sine 0 is 0. A cosine, or A equals 0 from that. Or you get A times 1 equals 0. And then from there, you use the same, now you have this equation here. You can plug in, you take the derivative, you get your Q1 dot. Q1 dot is equal to 0.525. You're going to find out that it should be, V will be equal to 0.525 divided by omega d1. Should be it. Because this cosine, this will become a cosine when we take the derivative. Cosine of 0 is 1. You get b. This is going to still be the 1. But when you take the derivative, this omega d1 comes out. So it's going to be b times omega d1 times sine equals your response at 0.25 divided by omega d1. Now you have b. And omega d1 is just what? 1 minus zeta squared?
Times omega.
Times omega. Okay, and 1. And that's just going to be your omega d. And so you're just using your